So in this session we are going to discuss about some question answer from the electrostatics chapters, and we will also discuss some concepts so that if you didn't go through this chapter you will get some idea, or if you have already gone through this then it will strengthen your concept. Okay, these are some important questions mainly for board paper, for NEET exam as well. Okay, so let's start. Given what is the charge on a body from which 1 million electrons are removed? Now, before solving this problem, I would like to describe one important thing, that is quantization of electron. Okay. Now, what is quantization of electrons? We all know that electrons presents as a multiple of some natural number, right? In a matter, we cannot have any root 2 number of electrons or any pi number of electrons. Yes, electrons or protons always stayed in a matter in some integer multiple. Yes, do we say something like this, that we have 3.14 number of electrons in a matter, or 3.14 billions of electrons in a matter? We don't say like this. Yes, either in a nucleus, either we say that there are 14 electrons or 16 electrons, which are all natural numbers. Okay, so whenever the quantity of electrons or protons come in a matter, we used to multiply the number of electrons with a natural number. Okay, so what is quantization of electrons is, we will say it is a integral multiple of E, where E is the charge on a body. Now, what is the value of E? Actually, E is the basic unit of charge, okay, or you can say elementary charge, which is given as 1.6 times 10 to the power minus 19 Coulomb. Okay, it is the value of E. Now, from now onwards, whenever you will be seeing this concept, that quantization of electric charge, then you can say that what it is a property of which the charge on a body is a integral multiple. Okay, it is a integral multiple of a basic unit of charge of an electron or proton, and that charge is represented by this symbol, and we all know that it is this. Okay, so let's say if a body contains in 1 number of electrons and in 2 number of protons, then what is the total amount of charge in that body? We have n1 number of electrons and we have n2 number of protons. So what is the net charge in that body? It is n2 minus n1 E. Yes, because charge on electron is negative and charge on proton is positive. Since the charge of electron is negative, and if we are removing electrons from a body, then what will happen? The body will be positively charged, because we are removing negative charge particles, that is electron. Yes, did you understand? Let's say we have this pen and it is now neutralized. It has equal number of protons, it has equal number of electrons. Let's say it has 10 million electrons, therefore it should have 10 million protons as well. That is why it is neutral. It does not possess any charge. Now what will happen if I remove electrons from this body? Only electrons. What will happen? Negative charge are getting removed. Then positive charge will, the number of positive charge is higher than the number of negative charge. In general we know that in general N2 equals N1, right? But what happens if N1 eliminated? If N2 greater than N1, number of protons increase number of electrons, what will happen? N2 will be greater than N1. This means N2 minus N1 will be greater than 0, and therefore this will be a positive quantity. So the net charge of the body will be a positive quantity. it will be a positively charged body. The body will be, so if we remove 1 million electrons from a body, what will happen? The body will turn from neutral to a positively charged body. Now the question is, what will be the charge of the body now? After removing 1 million electron, what will be its current charge? So as we know from the quantizations of electrons, Q equals in E, and we also know that E equals 1.6 times 10 to the power minus 19. On top of that, we are removing 1 million electrons. So 1 million is basically 10 to the power 6, right? 10 lakh, yes. So 10 to the power 6. So this amount of electrons are removed. So the charge of the body will be now 1.6 times 10 to the power minus 13 Coulomb. Okay, this will be the charge of the body. Given to find some comparisons between mass and charge. What is mass and what is charge? We all know this, right? Well, mass is basically a positive quantity of the body, right? And what is charge? Electric charge is defined on a body. It can be either positive, negative or zero. Okay? So let's write this: mass and charge. Mass is always a positive quantity, difference number 1. But charge can be positive, negative or zero, right? Charge of proton is positive, charge of electron is negative, and charge of neutron is 0. Yes. Number 2. Observe that we have learned this from the conservations of mass and energy, that mass of a body increases with its velocity, right? From this formula we know this, right? That if M0 be the initial mass, let's write this as mv. Actually, it's comes, if you have not learned this, maybe you will be learn this from later on in some advanced chapters, that the relations between mass and velocity is something like this. Okay, this is the initial mass. Let's write it as mi, so that it can represent properly mi. It is the initial mass and it is the dependency of mass upon velocity, and c is the velocity of light. Now observe that if v increases, then this mv is change. Okay, mv will decrease. So mass is depend upon velocity. Okay, but charge does not depend upon the velocity of the body. Another important point I have mentioned right now, that charge is quantized. Okay, it is always an integral multiple, but mass is not quantized, right? I will not write this, you can write this. Now, you know, as I mentioned earlier, mass, from the conservation principle of mass and energy, we knew that mass can be transferred into energy and vice versa. Energy can be transferred into mass. But this is not possible in charge. Charge is always conserved, okay? Charge is always conserved, but it is not conserved. Few more points are: mass can exist without charge. Okay, it is possible that there are certain mass. For example, you can consider any neutral body. It has no, its net charge is 0. So mass can exist without charge, but charge cannot exist without mass. Maybe the mass is very little, very negligible. Let's say mass of electron, it is very negligible, right? But it still has some mass. Okay, so mass can exist without charge, but cannot exist without mass. Okay, and I will give one final difference, that is the unit of charge in SI in the SI unit of charge is Coulomb, right? And what is the SI unit of mass? Unit of mass is a fundamental unit, right? Another important point is an accelerated charge emits radiation, okay? If you know electrons or protons, all this accelerated charge, they emits radiation. But an accelerated mass does not emit radiation, okay? I am writing this incompletely, but I am saying you should follow up the whole sentence and write it properly, okay? Let me repeat this once again, that mass is always a positive quantity, but a charge can be either positive, negative or zero. Mass cannot be negative, mass cannot be zero, but charge can be negative, charge can be zero. For example, electron, negative charge, proton, positive charge, neutron, zero charge. Charge does not depend on velocity. Whatever be the velocity, charge will remain same. But mass and velocity are interchangeable. If velocity increases at a significant amount, maybe close to light speed, okay, then you will see that velocity of that mass cease to zero actually, okay. It will not be zero, but it will be very close to zero. Now, from the conservation principle of energy and mass, we know that mass and energy are interchangeable. So mass is not conserved. Mass can be transferred into energy. Energy can be transferred into mass. Whereas charge is always conserved. Okay. Fourth point, mass can exist without charge. Take any neutral body. This pen, it has no charge, or its net charge is zero, but it has some mass. On the contrary, you consider any particle, any charged particle, they have some mass. However negligible it is, it has some mass. So charge cannot exist without mass. The fifth point, an accelerated charge emits radiation, okay? Accelerated charge emits radiation, but accelerated mass does not emit any radiation, okay? Coming to the next question, we have to calculate the force on an electron in a uniform electric field of 5 times 10 to the power 4 Newton per Coulomb. Here N stands for Newton and C stands for Coulomb, okay? And the direction is given as north because electric field is a vector, okay? So before solving this problem, I will briefly describe about what is electric field and what is uniform electric field. Okay? We all know from Coulomb's law that if you don't know Coulomb's law, I would suggest that you should read it first, but you can also follow this. After that, you can follow this. Okay? So what is Coulomb's law basically is? It describes the electrostatic force between any two charge. So Coulomb's law is something like this: F equals K times Q1 Q2 by R square, where Q1 or Q2 are any two charge separated apart of distance R. Let's say Q1 is the charge, Q2 is another charge, and the distance between them is R. So Coulomb's law is saying their interaction force or repulsion force, it can be two electrons, it can be one electron, one proton, it can be two proton. So if it is two electron, then it will be a repulsion force. If it is two protons, I mean if Q1 or Q2 are of same category, let's say electron or proton, then they will repel, right? They will not attract. But if Q1 or Q2 are one positive charge, another negative charge, one electron, one proton, then they will attract, right? So whether they attract or whether they repel, Coulomb's law is stating that if the distance between these two charged particles is r, then the forces between them which is called as electrostatic force, is something like this quantity, and we have some constant multiplied with this, which is called electrostatic force constant. Now this electrostatic force constant depends on the nature of medium separating the charges and also on the system of units. Now this K, which is a scalar quantity, it is a constant. The value of this electrostatic force constant, this K, this one, it depends on the nature of the medium separating the charges and on the system of units. What medium those charges are and in which system we are computing the force. For example, if we are calculating the force in CGS unit, then K is equal 1, okay? Or if we are computing in SI unit, then K equals 9 times 10 to the power 9. It is the value of K and it has some unit in Newton meter square by Coulomb square, okay? So what we observe, what we see, if the system change, if instead of SI unit we are calculating this force in CGS system, therefore in that case K will be equal 1. If you are computing in SI unit, in that case K will be something different. So the value of this electrostatic force constant depends upon the system, or it also depends on which medium we are, okay? If we are in vacuum, then K equals 1. If we are in some other medium, let's say we are in water, or if we are in hydrogen, or if you are in glass, then in that case K may vary from 3, 4, something like this, okay? So in different medium, the value of K is different. Okay, now, in most of the cases we will consider that we are in vacuum, okay? Just for the sake of simplicity, yeah? Now, coming to this problem. So this is Coulomb's law. And what is electric field? So electric field is something that describes the effectivity of a charge particle, okay? Let's say we have a charge particle here. Look, this green point. Now how much area does it cover? How long its effects are being covered? This is called its electric field. So you can say that given a charge, it permeates the space around the charge, okay? The space around the charge in which electrostatic force of attraction or repulsion due to, because of this charge can be experienced by any other charge. Let's say we have another charge here. Let's say we have another charge here. So electric field of this green point or this green charge is in fact it is the space around this charge in which electrostatic force of attraction or repulsion due to this green charge can be experienced by this orange color charge, okay? If this orange color charge, let's say this orange color charge are 1 meter apart from this green color charge, and this orange color charge are experiencing some disturbance because of this charge, either attraction disturbance or repulsion disturbance, then in that case we will say that the electric field of this green charge is at least 1 meter, at least. It can be more, we don't know, but it is at least 1 meter, because staying at least 1 meter apart, this orange color charge is experiencing its disturbing. But let's say this orange color charge is staying 1 centimeter apart from this green charge, and it does not experiencing any disturbance from this green charge. Then in that case we will say that the electric field of this green charge is at max 1 centimeter. It can never be more than 1 centimeter, but it is at max. We don't know, it can be less than, maybe it is 0.5 centimeter, but we don't know, that we have to compute that how much, but it is at max, we will say at max, okay? So this is the definitions of electric field. Now we need to learn one more thing in order to solve this problem, that is electric field intensity. So the electric field intensity is defined as the ratio of this force vector, it is a vector, right, by Q. Now what is Q? Well, first I will state the definition. You can note it down. Electric field intensity at any point is the strength of electric field at that point. I repeat, electric field intensity at any point, let's say we have a point here P. Now electric field intensity at any point P is the strength of electric field at that point. That is, it is the strength of electric field of that point. If the strength is higher, then electric field will be higher. If the strength is low, then electric field will be low. And how it is defined? It is defined as the ratio. Or we can say that it is defined as the force experienced by unit positive charge placed at that point. Let's say we have a unit positive charge here. We have a unit positive charge here, let's say Q. So it is defined the force experienced by this unit positive charge placed here, okay. Mathematically, it is written as the ratio of F vector and Q. Q is a scalar. Since F is a vector, therefore electric field intensity is also a vector, okay. Its direction is depending upon F, okay. If you have any doubts, let me know in the comment section. Now we have to calculate the force on an electron in a uniform electric field. Uniform electric field means in each and every direction the effect of the force is same, okay. So how to compute this? Now observe that we know the electric field, the value of the electric field is given, right? It is this quantity, its direction is given along north. We have to calculate F, right? We have to calculate force. Yes, we have to calculate F. Now we know E. We know Q because given it is an electron, we know the charge of an electron, right? You have to calculate F. So from here we obtain F equals QE. I am removing the vector symbol for the time being, but in the final answer we will write this, okay? Now we know Q is, what is the value of Q? Q is minus of 1.6 times 10 to the power minus 19, right? Times this 5 times 10 to the power 4. If we simplify this, 5 times 1.6 is 8 and we have a minus here. So it is minus 8 times 10 to the power minus 15. Since E is along north, so it is north. Along north, okay. Now we have a minus symbol here, so you can write 8 times 10 to the power minus 15 minus of north, which is south, okay. So the force is 8 times 10 to the power minus 15 along Newton, because force unit is Newton along south, okay. Next question is, we have to find that which one is bigger, a Coulomb or charge on an electron. So it is pretty simple. We have already seen that charge of an electron E is 1.6 times 10 to the power minus 19 Coulomb, okay. So definitely charge on an electron is far less than 1C, okay. So 1C is bigger and bigger than charge on an electron. It is a charge on an electron, so I am not using any symbol. And the next one is, how many electronic charges form 1 Coulomb of charge? So how many electronic charges form 1 Coulomb of charge? So we have 1 Coulomb of charge, let's say this as Q, and we know E equals 1.6 times 10 to the power minus 19C, right? We have to find the value of N, how many electronic charges. So definitely we are going to use the quantization of electronic charges formula. From here we obtain n equals Q by E. We have the value of Q as 1 and E as 1.6 times 10 to the power minus 19. Simplifying, we obtain 0.625 times 10 to the power 19. So this is basically 625 times 10 to the power 16. Okay. So around 6 million, right? How much positive and negative charge is there in a cup of water? So let us assume the cup contains 250 cc of water. Okay, we are assuming it. This is the volume 250 cc. So the mass of this water is 250 gram. Because density of water is 1, we are assuming density is 1. Now what is the molecular weight? This is mass. Let's find its molecular weight. What is the formula for water? H2O. So molecular weight will be 2 plus 16 equals 18. Yes. And next, how many molecules are present in this molecular weight of water? 6.023 times 10 to the power 23 number of molecules are present in 18 gram of water. Okay, it is Avogadro hypothesis. Therefore, number of molecules in 250 gram of water is 6.023 times 10 to the power 23 times 250 by 18. So this is the number of molecules in 250 gram of water. Let me repeat the process once again. We have to compute the total number of positive and negative charge in a cup of water. Okay. So in order to find the total number of this positive or negative charge, we need to find that how many molecules are present in that cup of water, right? Because electrons and protons are present in the atoms only, right? So for that we need the number of electrons, we need the number of atoms, we need the number of molecules. So first of all, what we did, we first extract how many molecules are present in that cup of water. That is our first duty. We need to first evaluate that how many molecules are present in that cup of water. Only then we can determine that how many atoms are there, how many electrons or protons are there. Okay. Now for that, what we did, we first assumed that, let's say, the volume of that water is 250 cc, and since water is assuming the density of water as 1, because in NDP the density of water is 1, so the mass will be same as the volume. Now next we calculate the molecular weight of water, which is 18 gram, we know. Now how many molecules are present in that water? Then from Avogadro hypothesis we know that number of molecules in a 250 gram of water, from Avogadro hypothesis we know that since molecular weight is 18 gram, therefore number of molecules present in that 18 gram of water is 6.023 times 10 to the power 23. So this much molecules are present in 18 gram of water from Avogadro hypothesis. Now how many molecules are present in 250 gram of water, that is that cup of water? For that we need to multiply that quantity with 250, which is this quantity, right? Which is this quantity. So what will be our next job? Our next job will be to find the number of electrons present here. Okay. Now each molecule of oxygen contain 8 electron, and each molecule of hydrogen contain 1 electron. Now we have two molecules of hydrogen and 1 molecules of oxygen. Therefore each molecule of water will contain 2 plus 8 equal 10 electron, right? Therefore total number of electron presents at each molecule of water will be, let me write this, total number of electron presents at each joule of water is 10 times 6.023 times 10 to the power 23 times 250 by 18. Yes, this simplified to 8.365 times 10 to the power 25. Okay, so this is the total number of electrons present at each molecule of water. So basically this is our N, right? So this is our N because it is total number of electrons. Yeah. Now we know that Q equals NE, right? Therefore we know N, we know E, we have to find Q. So by simply multiplying N with 1.6 times 10 to the power minus 19, this will gives us the total charge. Okay, so this is basically 8.365 times 10 to the power 25 times 1.6 times 10 to the power minus 19. This is 1.338 times 10 to the power 7 Coulomb. So how much positive and negative charge are there? It is 1.338 times 10 to the power 7 Coulomb. So let me repeat once again what we did here. We first assume that the cup of water contain, the volume of that water is 250 cc, which is equivalent to 250 gram because density of water is 1. Next, we calculate the number of molecule presents in that gram of water. Next, we find the number of electron present in that same quantity of water. Now, we simply multiply that number with charge E, and from there we obtain the quantization Q, that is the number of positive and negative charge present in that water, which is this one. Okay. Is Coulomb's law in electrostatics valid in all situations? We have seen Coulomb's law, right? Now the question is it valid in all situations? Well, the answer is no. It is not valid. No, it is not valid in all situations. Okay, so when it is valid and when it is not valid, we will see that. So Coulomb's law is valid only in this following situation. In situation 1, the electric charges must be at rest. Situation 2. Now there is another most important point when Coulomb's law does not valid is, let's say the size of the nucleus or the diameter of the nucleus, let's take this as A, and we have two charge Q1 and Q2. We need to take Q2 a little bit closer. Yeah. Assuming the distance between this as R and this R is less than A, that is, the two charges are separated with a distance R which is less than the diameter of the nucleus. In this case also, Coulomb's law will not valid, because what will happen is, if Q1 or Q2, two charges whose distance, since it is less than A, therefore these two charges can lie inside a nucleus, and what will happen is, the inside force of this nucleus, the nuclear force basically, okay, this will create a huge impact on the forces between these two charges. That is, the nucleus force will create a huge impact on these electrostatic forces between two charges Q1 and Q2. So in this case also, Coulomb's law will not be effective. So what I am trying to mean is, let's say we have two charge, okay, Q1 and Q2, if they are separated by a distance that the distance is less than the diameter of the nucleus, or if they are staying inside of a nucleus, in that case we cannot apply Coulomb's law. Okay. So if the, or in other words, you can also think in this way, that if the size of the charge is greater than the distance between the two charge, listen carefully, size of the charge is greater than the distance between these two charge, size is greater than the distance, in that case we cannot apply Coulomb's law. Okay, so we will write here the electric charges should be point charge, that is, size of charges must be less than the separation between charges, than the distance between two charges, or separation between charges. Or you can also say that in this way, that the separation between the charges must be greater than the size of the nuclear. Otherwise, strong nuclear force may dominate the electrostatic force. So these are some cases where we cannot apply Coulomb's law. Given a point charge plus Q is placed in the vicinity of a conducting surface. Let's say this is the point charge which is present in the vicinity of a conducting surface. Let me draw the conducting surface with a different color. Let's say this is the conducting surface, okay, and this one is the point charge Q. Okay, so we have to draw the electric field lines between the surface and the charge. Now we know that actually electric field lines are always normal to the surface of the conductor. Okay, it is always normal of the surface of the conductor. So it will be something like this, or something like this, something like this. I mean, it will be perpendicular. Okay, these are all perpendicular. Okay, normal means perpendicular, yeah, and it will go in this way. Yes. Okay, so always remember that electric field lines is always normal to the conducting surface. So it is given that a glass rod rubbed with the silk is brought close to two uncharged metallic surfaces in contact with each other, including charges on them as shown in this figure. Okay, so you have to describe what happens when the spheres are slightly separated and the glass rod is subsequently removed, and finally the spheres are separated far apart. So there are three different parts of this question. So we have this figure, and there is a glass rod that is rubbed with silk. So this glass rod is charged. Okay, it is positively charged, and there are two spheres A and B. So we know that since the glass rod is positively charged, therefore all the positively charged particle A will repel this glass rod, right? Yes. So it will try to escape from this surface and it will move towards B, right? Because distance of, B is staying farther than this glass rod, than this positively charged glass rod, right? Since there is a repulsion, therefore the positively charged will stay away, will move away from this rod. Okay. Now, what will happen if the spheres are slightly separated? So let's say this is sphere 1 and this is sphere B now, and the glass rod is still there, which is positively charged, and we have this negatively charged here, and positively charged will remain fixed. Well, the question is why it is so? Why here it is negative charge? Well, it is negative charge, it is clear, because the glass rod is still in the same position, but the spheres are slightly separated. So basically what will happen is, in this case, since their connection is broken now, right? Earlier these two spheres were connected, but now their connection is broken. So when they are connected, what is happening is the positive charge is flowing from A to B. It is possible the charge distribution is possible from sphere A to B when they are connected. Yes, positive charge are flowing from the surface of A to the surface of B because they were connected. But now this connection was broken. Okay, because they are separated now. So what will happen is the charge are trapped actually. Yes, the charge are trapped. So the negative charge will freeze, the positive charge will freeze with respect to their earlier position. So for that reason, positive charge here will freeze, the negative charge here will freeze. There should not be any changes between this, but there will be some changes at this surface and on this surface. Yes, so what will be the changes? Since we have a negative charge here, so this part will be positively charged, and since we have positive charge here, so this part will be negatively charged. So now the thing is that what will happen if the glass rod is subsequently removed? Now if I remove the glass rod, what will happen? Let's say there is no more glass rod. So think yourself that does it really affect these two charge object, because this object are already charged now, they are now charge object. Okay, now if I remove the glass rod, this will not affect anything on these two spheres. Okay? Yes, these two spheres are now charged, they are now charge object. So removing the glass rod will not affect this sphere A and B. Whatever they were in this state, they will remain same in state 2 as well. Okay, now what will happen if the spheres are separated far apart? This is the interesting thing actually. If the spheres are now quite far actually. Now as I mentioned, these two spheres are now charged object. Okay, they are now charged, they are no more uncharged, they are no more uncharged. Okay, they are charged now because we didn't perform any grounding or earthing kind of thing. We didn't leak their electrons. Okay, we didn't perform anything so that they remain uncharged or some kind of leaking happened. Since there was no leaking, so sphere A and sphere B will remain as it is. But the thing is, they are now separated far apart. So in this case, what will happen is, they will definitely behave like an independent charge conductor, right? Since earlier sphere A was, because of the rod, sphere A was negatively charged. The negative particle, the negative charge particle was increased in A and positive charge particle was increased in B. This was the earlier condition. So because of that reason, A will retain with negatively charged object and B will retain with positively charged object. Okay, since we have no glass rod is present to influence their charges, and sphere are also far apart, so charge distribution is also not possible in this case. And because of think about the first stage of the experiment, because of the glass rod, A was, the induced charge on A was negative, and because of this connection, the induced charge on B was positive, and with that we have separated the sphere. Then gradually we remove the glass rod. So and we also didn't perform any leaking or earthing. So A will remain same as what it was earlierly charged. A was negatively charged and B was positively charged. So these two sphere will remain, will behave independently charged conductor. They will act as a separate induced charge conductor. Okay, so if you have any doubts in this problem answer session, let me know. I hope lots of your concepts gets clear. A plastic rod of length 2.2 meter and radius 3.6 millimeter carries a negative charge of 3.8 times 10 to the power minus 7 coulomb spread uniformly over its surface. We have to compute the electric field near midpoint of the rod at a point on its surface. So, this is the rod length 2.2 meter and the radius here, it is diameter. So, the diameter is 7.2 millimeter. Okay, that is the radius is 3.6 millimeter. So, what we have to find is, let's say this is the midpoint, so this point is the midpoint. We have to find the electric field on its surface, at M. Let's say M with the midpoint on its surface, we have to find the electric field at M. Okay, this is a thing actually we have to do. Now, how we can solve this problem? See, conceptually it's a very important problem because we will get to learn lots of things in order to solve this problem. Okay, whatever we have did till now using those concepts, it is not possible to solve this. The most important thing that we need to learn before solving this is Gauss theorem on electric flux. So what it is? So I will not go into the details. Basically, it is saying that the total electric flux over a closed surface. Let's say we have a closed surface. It is a closed surface S, and Gauss theorem is stating that the total electric flux over this closed surface is 1 by epsilon naught times the total charge contained inside this surface. Okay, this theorem is usually denoted mathematically in this way. You may not be familiar, I hope that you guys are not familiar with this symbol or not even the integral symbol. Well, this is the integral symbol, okay, that you will be learning in calculus. And whenever we are using this circle kind of thing, it is called integral over a closed surface. Okay, it is surface integral. Surface integral is not in your syllabus in class 12. We will learn this in your BTech. So Gauss theorem is something like this. Okay, this is Gauss theorem, mathematical expression. This is the electric flux. This is denoted as electric flux. Electric flux over the closed surface S, and we can obtain this total electric flux over the surface is total charge inside S by epsilon naught. Epsilon naught is a constant. We are assuming that we are in vacuum, okay, or at least in air. Otherwise, this epsilon naught will get changed. Yes. So this is what Gauss theorem. Now the thing is, why I am bothering so much about Gauss theorem? How Gauss theorem is related with this problem? The thing is, with the help of Gauss theorem, we can prove. Gauss theorem has lots of applications actually, okay, in the field of electrostatics. And one of the most important application is Gauss theorems. With the help of Gauss theorems, we can show that electric field due to an infinitely, let me write this here, electric field due to an infinitely long straight wire is something like this. Electric field is E. It is E equals lambda by 2 pi epsilon naught R. I am not going to prove this here, but this proof is also not in your syllabus, but we can obtain. Let's say we have an infinitely long straight wire. Therefore, with the help of Gauss theorem, with the help of Gauss theorem, we can obtain this, we can derive this electric field, this expression, okay. That is the importance of Gauss theorem. So here lambda is linear charge density, because we are in a straight rod, yes, linear charge density. We are not over any surface, so that's why we are taking linear charge density. And r is the radius of the wire, because wire is a cylindrical kind of thing, right? So it is the radius of the cylinder. Now the thing is, how we are going to use this in order to solve this problem. First of all, I would like to bring your attention that whenever it is, in this expression, or in this statement, we have mentioned it is the rod should be, or the wire should be infinitely long. It means, see, practically infinitely long is not possible, right? But we can assume that if the rod or the wire is very large compared to the radius, it is very large. For example, in this problem, right, 2.2 meter, it is quite large, it's huge, right? So in all those cases, we can apply this formula actually, okay. It is safe to apply this formula. So we will apply this formula here to compute the electric field, to compute E, okay. So let's compute it. Now we know that our E will be, back to this problem now, E will be lambda by 2 pi epsilon naught r, okay. We know, see, denominator is known, the value that is given in the denominator is known, right? All we have to evaluate lambda. So let's first substitute the value of what we know in the denominator. Yes, it is 2 pi epsilon naught. The value of r is 3.6 millimeter, which can be written as 3.6 times 10 to the power minus 3. I am converting this into SI, okay. This equal 2 lambda 4 pi epsilon naught times 3.6 10 to the power minus 3. Now we know that 1 by 4 pi epsilon naught equals 9 times, yes, 9 times 10 to the power 9. So this gives 2 lambda times 9 times 10 to the power 9 by 3.6 times 10 to the power minus 3. So what we have to do now, we have to find lambda. Now lambda is linear charge density, right? And we know lambda equals Q by L, yes, where L is the length of the rod. Now what is Q here? So instead of computing here, let's substitute the value here, okay. So we have 2Q times 9 times 10 to the power 9, and L, or L is 2.2 times 2, or Q is negative charge, right? So there will be, we have a minus in the forward, so 2 times 3.8 times 10 to the power minus 7 times 9 times 10 to the power 9 divided by, we have denominator. This is the thing actually, okay. Now if we calculate this, we will obtain, this is approximately this one, minus of 8.6 times 10 to the power 5, and E, the unit of E is Newton per Coulomb, okay. So we have this. Okay, so we have minus 8.6 times 10 to the power 5 Newton per Coulomb, and minus symbol signifies that the direction of electric field E is a vector, right? So here negative symbol signifies that direction of E at any point will be radially inwards, okay, radially inwards. A large plane sheet of charge having surface density this much, lies in xy plane, a large plane sheet of charge, it means we can assume that it's an infinite plane sheet. So again, the applications of Gauss theorem will come here. I will discuss that. So what we have to do is we have to compute electric flux through a circular area of radius 1 centimeter. Given normal to the circular area makes an angle 60 degree with z axis. Okay. Before coming to the second part, let's discuss about the first part. We have a large plane sheet. It means we can consider that it's a very large, almost infinite large. Okay. So how to obtain the electric field? So we need to first obtain the electric field over this sheet, right? Only then we can compute the next part, okay? Because that circular area is inside that sheet, okay? So how to compute that one? Well, again, we have another applications of Gauss theorem, that is, I will just write the final answer here, that electric field intensity, that is E, let's write this as E. Electric field intensity, E vector, due to a thin infinite plate sheet is something like this. It is the magnitude, okay? It's sigma by 2 epsilon naught, where sigma is, yes, surface charge density, yeah. So if we have a thin infinite plate sheet of charge, then the electric field intensity over that surface is this expression, okay? Using these equations, we can obtain the electric field density over that surface at any point of the surface. So this is obtained from Gauss theorem. So from here we can obtain, we have the surface density is given. So from here we can obtain E because we know sigma, yes. Now the thing is, we have to compute the electric flux through a circular area of radius 1 centimeter. Now before moving to that, I want to write one expression here, that we all know that electric flux act normally along any surface conductor, right? But not all surfaces are conducting surface, yes. If you have a conducting surface, then electric flux will act, electric field lines act normal, right? Electric field lines act along normal to a conducting surface, but not every surface is conducting surface, right? So in that case, how to compute electric flux? Because the thing is, electric flux is computed as something, in a conducting surface, we know the electric flux is computed as E times S, where S is the surface area of that conducting surface. Let's say we are computing in a very, small part. So this is the formula for a conducting surface. Now not every surface is conducting surface, right? So in that case, how to compute electric flux? Well, the electric flux that is defined as delta phi over any surface is defined, can be computed using the help of this formula, okay? It is E dot delta S. Let delta S, where this delta S is a surface area of a small surface, okay? Using this dot product, we can compute delta S. Now what is this, the thing is, delta S is a area, right? So it cannot be a vector, but E is a vector, and here we are using dot product, so delta S should be a vector. So in physics, we define delta S vector like this. It is n vector and delta S, where it is the surface area. This is the magnitude and this is n vector, that is normal. So let's say we have a surface here. Let's say this is delta S. So this is normal n cap. So delta S vector is defined like this. Is it clear? Let me repeat once again. Let's say we have a very small surface here, any surface, and we take a normal on that surface, a normal vector n cap. So delta S vector is the small area, the magnitude of that small surface times n vector. Okay, so it becomes a delta S vector. Now, once we know this, we can compute the electric flux of this small surface using this expression, using this equation. Okay? So, here we obtain this equal, since it is a dot product, so this is basically E delta S cosine theta, where theta will be the angle between n cap and E vector. Okay, theta will be the angle between n cap and E vector. This is theta. Angle is not between the surface, angle is between the normal. So, if theta equals 0, then E is max. That is, in case of conducting surface, we know that E acts normally along conducting surface, and when theta is 90, that is when E acts along the surface area, it is electric flux is 0, minimum. So, electric flux is maximum when E acts normally, and electric flux is minimum when E acts along the surface area. Electric flux is maximum when E acts along normal, electric flux is minimum when E acts along the surface area. So basically this is the formula to compute electric flux. Okay, whenever you will encounter the computation of electric flux, you have to use this formula, E times delta S times cos theta equals to delta phi. Electric flux is a scalar, yes. Now we know E, yes. We know delta S because from here we can compute. We have given radius 1 centimeter. We also know theta, yes, because 60 degrees is given. Makes an angle with z axis and z axis will be the normal, right? Because it is in xy plane, yes. So theta equals 60. We have this. So delta phi is equal sigma by 2 epsilon naught times pi times cosine 60. Now quickly calculate this value and evaluate electric flux, which is equal 5 times 10 to the power minus 16 times 2 pi square times cosine 60, right? I simply multiply with 2 pi in the numerator and denominator to obtain 4 pi epsilon naught in the denominator, because we know the value of this one. And this equal 5 times 10 to the power minus 16 times 2 pi square, and we know cosine 60 is half, so this 2 will get cancelled out, times it is basically 1 by 4 pi epsilon naught. This is basically 9 times 10 to the power 9. Okay, now this is 45. Now if we calculate this, let's calculate with the help of calculator. So this will be 10 to the power 9, 10 to the power minus 7. I think I made some mistake. Oh, it is 1 centimeter. So it will be, yeah. So it will be, we have to convert this into SI. So it will be, let me use this one, it's a mistake here. It is 1 centimeter, we have to convert this into meter. So basically this is 10 to the power minus 2 square times cosine 60. And here, so here it will be 10 to the power 4. Yeah. So it is minus 20. Yeah. So we have 5 times 10 to the power minus 20 times pi square times 9 to the power 9 to the power 9. So if we compute this is basically approximately, it will become around 4.44 times 10 to the power minus 9. Okay, and flux, what is the unit of flux? Flux is basically E times surface area. So Newton per Coulomb is E, and meter square for this one. So it is Newton meter square per Coulomb. Okay. Why no two electric lines of force can intersect each other? First of all, we will learn that what is an electric lines of force basically, okay? Well, you know, it is basically an imaginary lines. It does not exist in reality, but it is just some thought of abstract thought, okay? It was first originated by Michael Faraday in order to describe the directions of electric field. So basically, electric field lines are imaginary lines that are basically used to represent the direction and strength of an electric field around electric charges. Okay, so you can think they give a visual way to understand that how electric force act in a space. The more dense the electric field lines are, the more strong the electric field. Okay, and if they are not showing dense in this way, then it means the electric field is very weak. Okay, now is it possible that two electric lines of force can intersect each other? So let's say we have two electric lines of force, they intersect each other. Okay, so what will happen? The point at, what will be the charge of this intersecting point? It has, its electric field has two direction, yes, which is not possible, right? A charged particle can have the direction of the electric field of a charged particle should have only one direction. It cannot have two direction, two different direction. Therefore, it is not possible. Okay, so this is not possible. Now the next one is an important question, that is a charged particle free to move in an electric field? Well, the answer is no. A charged particle is not free to move in an electric field. A charged particle is free to move an electric field only if the particle is at rest. If the particle is at rest, then there is no problem. But what if the particle is not at rest, the particle is moving? By the way, I am considering here positive charge, but you can also draw similar conclusion for negative charge. Only you have to change the direction. Okay? Because in the definitions of electric field, we use positive charge. Yes. So let's say a positively charged particle enter into this electric field. If the particle is at rest, as we have seen, whether positive or negative, it will take the directions of the electric field. It will obey the rule of this electric field. But if the particle is not at rest, if the particle is moving, let's say we have a positive charge, it's a moving particle and it's entered into an electric field. So what will happen in this case is, well, in order to understand this matter, again, back to this thing that electric field lines are imaginary lines and that represents the direction of the electric field of each point in space, right? Let's say we have a curved electric field here. So the direction is obtained by the tangent, okay? Electric field lines are straight line, but if we have a curved electric field, then we obtain the direction at any point through its tangent. I will discuss this in more details, but for the time being, electric field lines, as we have seen, is a straight line. If we are in curved electric field, then it will be a tangent. If the electric field is straight, then it will be the straight line. Now, what happens if a positively charged particle enter into an electric field? If the particle, let's say this is the particle, enter into an angle into this electric field. Let's say it makes an angle to the it makes an angle theta with the electric lines of force inside this field. Okay, then it is, in general, it will not continue along the field line. Okay, it will take some different direction because it will experience a force in the direction of the field. Let's say we have these electric field lines and it enters at an angle, say theta. Okay. So what will happen is this particle will experience a force in the direction of the field. Since it is experiencing a force as soon as it enters in an angle with these electric lines, then it will then it will experience a force, and as soon as it experiences a force, then according to Newton's law, its velocity will get changed. Yes, its velocity will change because of the force, because of the experienced force. Yes, because there will be some sort of acceleration, and this will give some changes in velocity. So we can say that the particle will not move along the electric lines of force if the particle is moving, whether it is positively charged or it is negatively charged. If the particle is not at rest, it will not move along the electric lines of force. Okay. So long story short, you can say that, the path of the particle, the path of the particle is determined mainly by two factors. Let's say a positively charged particle enters into this electric field, or any positively charged particle enters into this electric field, whether it is rest or it is moving, its path will mainly depend upon these two factors. Then the factors are its initial velocity and the force due to the electric field. Okay. So do I need to repeat it? So let's repeat this. For the first answer, we have seen that can two electric lines of force intersect each other? The answer is no, because we are getting two different directions of this particle, of the particles situating at the intersecting point. So it is not possible because electric lines of force has only one direction. A charged particle is free to move in an electric field? Well, the answer is no in general. If the particle is at rest, and if the particle is positively charged, then it will move along the directions of electric lines of force. If the particle is positively charged, then it will move along the electric lines of force. If the particle is negatively charged, the particle is at rest. I am talking of the particle is at rest. Now, if the particle is at rest, so there are two conditions. If the particle is positively charged, then it will move along the electric lines of force, and if the particle is negatively charged, then it will move away from the electric lines of force. Yes, because it is negatively charged. So we will fix our discussions on positively charged particle only. Now, what happens if the particle is moving? So if the particle is moving, then it may not move along the electric lines of force, because it is definitely good, because there are high chances it can enter into the electric field with some angle with respect to the electric lines of force in that field. And if it is entering into an angle, then it will encounter a force. And from Newton's law, force gives acceleration. Acceleration means changes in velocity. Yes, and since changes in velocity, therefore chances are almost nil that it will move along the electric lines of force. It will create its own path over the time. Okay. So we can say that, in short, that the particle, the path of the particle mainly depend upon these two things: the initial velocity of the particle and the force due to the electric field. Okay. Next question is, what does Q1 plus Q2 signify? Well, before having discussions on this, I would like to describe about electric dipole. Okay, what is dipole? So basically, an electric dipole is something like this. Let's say, we have an electric field. It consists of a pair of equal and opposite point charges. Okay, so this is what electric dipole, and they are far apart. Let's say a distance, say a. Okay, so this system is called as electric dipole. So what is electric dipole? An electric dipole consists of a pair of equal and opposite point charges separated by some small distance. Okay, this A is quite small. So this is what we call as electric dipole. Two equal and opposite charges separated by a small distance. So now, what does Q1 plus Q2 signify? Now observe that if we add these two charges, it is 0, right? So the same thing is here as well. So Q1 plus Q2 equals 0 signify that that it is a system of point charges which is called as electric dipole. It is a pair of equal and opposite charges. If Q1 is positive, then Q2 is negative. If Q2 is positive, then Q1 is negative. Okay, so it is a pair of equal and opposite charges separated by a small distance. Yes. Now the second one is, define the term electric dipole moment. Is it a scalar or vector? Well, electric dipole moment is the product of these two charges, plus Q times minus Q, definitely we have to take the mod, times the distance between them. Okay, this is electric dipole moment, which is usually denoted with P, the small letter p. So basically P equals, you can say it is some kind of a q. Okay, sorry, here it will be one q, either plus q or minus q, mod of this. So this is basically electric dipole moment. So it is the product of either plus q or minus q, and then you take the modulus times the distance between the charges. So in this case we have distance a. So is it a vector quantity or scalar quantity? Well, it is a vector quantity, and since it is a vector, its direction is from minus q to plus q. Okay. Before moving further, let us discuss one important topic here, that electric dipole, how electric dipole behave in an external electric field. So the electric field can be uniform or non-uniform, but we want to analyze that how an electric dipole behaves in an external electric field. So for the sake of convenience, first we are assuming that if the external field is uniform electric field, it's an important type. So we consider a electric dipole, let's say A and B here. Let me use different color, green. We consider one electric dipole. We know all what is electric dipole. It is a pair of equal and opposite charges of distance apart, a very small distance apart. So let's say AB, distance between them, this one is 2a. Okay, and we have a positive charge plus q here and negative charge minus q here. So we know that the dipole moment, the magnitude of the dipole moment is the distance between them, AB times q. So it is 2a q. Okay, and its direction is from negative charge to positive charge, that is from B to A. This is the magnitude, and direction is from B to A, right? So what happens when this dipole comes in an effect of an external uniform electric field? So let's say the electric field is working like in this way, in this direction. Okay, so let's say this is E vector, and this angle, it is an oblique, so let's say this angle is theta. So what will happen in this case? Now notice one thing, that here we have to consider these two edge, consider these 2 points A and B. Okay, so at A we have a positive charge plus q, and at B we have a negative charge minus q. So what is the force here? The force at A, electric force at A, I was using green color for this one, so let's go back to green here. So force at A is, what is QE, right? Yes, Q times E, Q times electric field, and force at B is minus QE. So what is the net force on this dipole? Net force is QE minus QE equals 0. So net force is 0, right? Yes. Now observe one interesting thing here, that force at A is QE at this direction, but force at B is in in opposite direction, right? Because it is minus QE. Yes, opposite to E. Force at A is along E, QE, and force at B is opposite to E, minus of QE. Okay. So these are two unlike forces because they are parallel but in opposite directions, and we have learned in our maybe you have learned this in your class 11 that in rotational motion that unlike forces create a torque, right? So definitely here we have a torque. Then the surprising fact is net force is 0, but still we have a torque because of this unlike force, right? So how to compute this torque? If we have to compute this torque, how we can do that? Okay. So in order to compute the torque, what we need to know? We need to know that, what is the definitions of torque? Torque is denoted by tau. The definition is force times, I am talking about the magnitude first. Let's say this is the magnitude of the torque. How to compute? It is force times arm of the couple, right? Yes, this is the couple. Force at this direction is so it's a couple here. And what is the arm of couple? How to compute arm of couple? If AB is this, the arm of the couple means it is the perpendicular of the force, right? Perpendicular of the force, arm of couple is defined as perpendicular of the force, and the force is in this direction. So if we say C, if we draw a line AC perpendicular to E, E is this, right? This is also E, this is minus E. So if we draw a line perpendicular to this E, then we will get the couple. Yes, and since this is theta, so this is also theta. Yes, this is B. B is here actually. Okay. Now, how to define? What is AC? So this first let right. So force. So what is our force? Our force is QE, right? Yes, force is QE, and times arm of the couple, that is AC. So QE times, and what is our AC? AC is AB sine theta. Okay. So from here we know the value of AB, right? AB is 2A. So this is basically 2A sine theta. Also we know that P is 2AQ, right? So this is basically PE sine theta. Yeah. So we obtain our tau as PE sine theta. So in a uniform electric field, the torque upon this upon this dipole is PE sine theta, where theta is the angle between the dipole and the electric field. Okay. Now we will do some cases here that what will happen if theta equals 0, if theta equals pi, if theta equals pi by 2, because we have sine theta here, right? So coming straight forward, at theta equals 0, what does it implies? It implies the angle between the electric field and the dipole is 0. So the dipole is along E. Yes. So in this case, tau equals 0, and this is called stable equilibrium. Okay. And what is theta equals pi by 2 in this case? This is maximum, right? Sine is maximum when theta equals pi by 2. So tau equals PE. So we have the maximum torque upon this moment. But what about this 2 when theta equals pi? Well, in this case, what will happen is the moment will be antiparallel, opposite to E, right? It will be opposite to E. Now, since the force is opposite, so what will be the tendency of the force? The tendency will be to align it with itself, right? What will be the tendency of the force? The force is along E. The force is along E, right? So this is our E. sorry, this is the, let's consider this as the dipole and this is the E, and E is in this direction, okay. But if the dipole goes in this direction, so the tendency of the force will be to make it is along E, okay. So we can say that at this position the system is unstable, okay. It is an unstable equilibrium because it is acting completely opposite to the force, but force will not accept that. Force will try to align the dipole according to its direction. So it is an unstable equilibrium, okay. So this is about uniform electric field. But what if we are in a non-uniform electric field? Well, we will not go into too much deeper about non-uniform electric field. We will only consider some particular cases. Say for example, if the force in the if the electric field acts, all the electric fields. See, there are several reasons when electric field can be a non-uniform electric field, right? For example, the forces are acting in different directions. The magnitude of the forces are not equal, okay? Because force is a vector. Even if the magnitudes are equal, but the directions are different, so still it is a non-uniform electric field. So we will not dig deeper in this. We will just consider some simple cases. That is also in your syllabus, and those are not in your syllabus. So the interesting thing that we will be considering here, that let's say the magnitude of the forces are different. Okay, the strength of the forces are different, and with this and assuming this, we will consider two particular cases. But the case one will be, we will consider that the forces are acting along P. Case 1 and case 2 will be forces are acting opposite P. So what is our P? P is our electric dipole moment, and P acts, direction of P is from negative charge to positive charge. So the electric field, we will consider two cases. The electric field either acting along P or acting opposite to P. So in both the cases, the electric field, let's say E, since we do not have uniform, since in this case our electric field is not uniform, so let's say E is the resulting electric field, because electric field is a vector. So if E vector is acts along P, so what will happen in this case? Net force is not equal 0, but tau equals 0, because angle between E and P is 0, right? And because sine 0 is 0. But net force is not equal 0 because the forces are not equal. Yes, force at A is not equal force at B. So the net force is not equal 0. But if E vector acts opposite P, same conclusion, the net force is not equal 0, but tau equals 0. Now the thing is, in which direction the net forces is acting in both of these cases. Since net force is not equal to 0, the torque are 0 in both the cases, but the net forces in this case is also not 0 and in this case also not 0. So in which direction is the net force is acting here? So let's say we have a force. We can see this very easily actually. It is very easy to compute. Let's say the force, let's say the electric field at A be E1 and the electric field at B be E2, okay? Since they are acting along P, so the net force will be something like this: Q E1 plus Q E2. This equal Q E1, sorry, it will be minus, because the charge is minus Q at B, right? So it is E1 minus E2. Now, what is the directions of E1 minus E2? Since E1, E2 are parallel and E1 minus E2 is a positive term, therefore E1 minus E2, the directions of E1 minus E2 will be along E1. Yes, it is along E1, and both E1 and E2 are in the directions of P. Yes, because it is acting along P. Therefore, the net force in this case will act along P. Similarly, we can also derive this, that the net force in this case will be opposite to P. Yes, because in this case we have minus of QE1 plus QE2, because the directions of E1 in this case is opposite to P, so we will write minus of E1, okay, and this gives us Q E2 minus E1, and since this is a negative quantity, therefore it is along minus of P, therefore it is opposite to P. The net force acts opposite to P, okay. If you have any doubts in understanding this, let me know in the comment section. Yeah. Draw a graph to show the variation of electric intensity E with perpendicular distance r from an infinite line of charge density lambda coulomb per meter. Evaluate work done in bringing a charge q from a perpendicular distance r1 to r2, where r2 is greater than r1. So there are two parts in these questions, right? Part 1 is we have to draw a graph to show the variation of electric intensity E with perpendicular distance r from an infinite line of charge density lambda coulomb per meter. So let us assume that we have a very long wire, okay. We are assuming the length of the wire is finite, say L, but L is very large, but we are also assuming that the electric intensity is spread out along its axis infinitely, okay. So why we are doing this, you will understand it very soon, but simply follow up the discussion, okay. So I hope till now everything is clear. We have assumed a L length of a circular wire, a cylindrical surface. Circular wire means cylindrical surface. I mean a cylinder of very small radius. Okay? And we also assume that the electric field intensity is spread infinitely along its axis. So now let's do one thing. Let's take a small. Now first let's take a. So let's say P be any point here. Okay. And we consider a very small line element. Let's take this as some origin, and we consider very small. Say this is dl1 and say this is dl2. We consider very small line element on this wire. Okay. Now the thing is, since we are in a uniform, I mean the charge density is uniform, right? Lambda coulomb per meter. We have uniform electric field. So what will be the effect of this small line element over, I mean at this point, both dl1 and dl2? Let's say it has because of dl1, let's assume the electric field be E1, and because of dl2, let's say the electric field be E2, okay. So this is E1 and this is E2, okay. Now if we now find out the component of E1 and E2, where will be their component? Their component will be something like this. It is the component of E1 along this side. It is the component of E1. It is the horizontal component. It is the vertical component of E1. Similarly, for E2, we have, this is the component for E2, horizontal component, and similarly again this is the vertical component of E2. So observe that the vertical component of both E1 and E2 are coinciding, right? Their vertical components are coinciding, but their horizontal components are opposite to each other. And since we are in a uniform electric field, therefore this blue and pink one, this and this, they are equal and they are opposite, so they will cancel out. So what I am trying to say is that the electric field at P because of this two line element is along OP vector, along the radial vector, right? Along this radius, and its magnitude is depending upon the radial vector only. Yes, because this horizontal forces are getting cancelled out, and what remains is this vertical component. Horizontal components are getting cancelled out, what remains is vertical component, and this vertical component is along OP vector or along the radial vector, and its magnitude also depends upon this OP vector. Yes, so we can say that since we choose P as an arbitrary point, so we can say that at any point the electric field will be depend upon the radial vector, and its direction is along direction is along OP. Okay. Now, from Gauss law, we know that electric flux phi E is something like this. Yes, this we can write. This is actually surface integral over a closed surface, and we have assumed the wear is closed because it is a cylinder. So this is basically E vector time n cap ds, right? How ds vector is defined? It is n cap ds, yes, where n cap is along the directions of E vector, okay? And since here n cap and E are on the same direction, so this is basically E ds, and E is constant here, electric intensity is constant in this case. So this is E ds. And what is the surface integral of this cylinder? It is 2 pi RL. What is the surface area of a cylinder? 2 pi RL, right? So surface integral, that is the area. You will, if you don't know calculus, you will learn it in the calculus that surface integral denotes the area, surface area, okay? Surface area, since we have considered a cylindrical wear, we have considered cylinder of radius rho and length r. Cylinder, radius rho, length L, okay? So if we know the radius of a cylinder rho and the length of the cylinder L, then its surface area is 2 pi rho L. This is what here, surface integral, this is surface integral, and this is the surface area. This is Gauss theorem. Actually Gauss theorem, actually electric flux, actually this is electric flux, this is not Gauss theorem, sorry. This is the definitions of electric flux. Gauss theorem is stating that this equals Q by epsilon naught, where Q is the charge on the surface, net charge on the surface, okay. We will come to that part after some time, but this is Gauss theorem actually. Q is the net charge of this surface. In this case, our surface is a cylindrical surface. So this is Gauss theorem that surface integral of this thing equals Q by epsilon naught, where Q is the net charge on that closed surface. So for the time being, forget this part. We will need this after some time. But for the time being, try to understand this one. So electric flux is defined the surface integral of these two. Closed surface, we are in the closed surface, okay. In this case, we are in the closed surface, otherwise this thing does not exist, and from here we obtain this thing. Now from Gauss theorem, now come to the Gauss theorem, we can say this equal Q by epsilon naught, where Q is the net charge on the surface, total charge, net charge, okay. Now since we are in, the charge density is given as lambda Coulomb per meter, and we have assumed the length of the wear is L. Therefore, we know that Q equals lambda L, right? Yes. And this gives E times 2 pi rho L. Since our E is constant here, we are in uniform electric field. This is lambda L. This gives E equals lambda by 2 pi rho. Okay. sorry, there will be one epsilon. So this is the relationship between E and the radius of the circular wire. Okay. So this is a different part. We just obtain a relationship between E, electric field intensity, and the radius of a circular wire. Radius of a circular wire is inversely proportional with electric field intensity, because all these things are constant, right? We can write E varies as 1 by rho. Okay. Let us now come to this problem. We have to draw a graph to show the variation of electric intensity E with perpendicular distance r. So if we think that we have a wire of radius r, okay, assuming the same as what we have assumed here, the electric intensity is spread axial along its axial infinitely, okay, and let's say it is r and it is O and it is our P. Then we can say from here that electric field intensity this equal lambda by 2 pi r epsilon naught. Yes, did I make you understand? See what we obtain from here. E equals lambda by 2 pi rho epsilon naught, where rho is the radius of a cylinder of the circular wire. Now we have to calculate we have to see the variation, that with respect to r how E is changing. So for that, what we assume is we consider a r length of circular wire. Therefore, from here we can say that electric intensity at any point over this on this surface is something like this. Electric field intensity on this surface is something like this. Now what happened if r is changing? How can we compute E? So now we are no more on this surface. Our surface is changing. Let's say we are here, or we are here in this way, because r is now changing. So observe that this is some kind of rectangular hyperbola, right? This is some kind of rectangular hyperbola where this is axis E, this is axis R. Okay. So what we can say is the variation will follow this graph, this rectangular hyperbola graph. Okay. You know the equations of rectangular hyperbola? Yes. What is the equations of rectangular hyperbola? It is something like this. Xy equal 1. Yes. So it also looks something like this, right? Because lambda, 2 pi, epsilon naught are all constant. Okay. Or either this form or in this form. These are all rectangular hyperbola. C is not equal to 0. So the variation will be along this rectangular hyperbola. Okay. Now we have to evaluate the work done in bringing a charge from perpendicular distance R1 to R2. How much work done is required in bringing a charge from perpendicular distance R1 to R2. So let us now closely analyze this. Let's go to another page. So let us consider this wire against here once more, but in this time I am considering in a bigger form for the sake of understanding. We are focusing with the help of microscope. Okay? So let's say, and the electric field intensity are along this axis. Okay, it is infinitely spread out. So this is our origin. This is, let's say, any point. I mean, this distance is r, right? Let's say this is p. Okay. Now we have to compute the work done from R1. Say this is R1 level, and say this is, sorry, R1 was lesser, right? So it will be R2. From R2 level to R1 level. Let's say this one is the R1 level and this one is the R2 level. Okay. I mean this one is R1 and this one is R2. So you have to compute the work done from R2 to R1. You have to compute the work done of a particle from R2 to R1 of a charged particle. Charge is Q also given, right? Charge is given as Q. The charge is Q given, right? So what is the work done of a charged particle from R2 to R1? Now we know this E equal lambda 2 pi R epsilon naught at this point. At this point E is something like this. E is this, okay? Here R is constant. So let's do one thing. We take Ex equals 2 pi x epsilon naught, where x is varying from 0 to R. X will never be 0, it is strictly positive, but it is less than equal to 1. So here, what is the advantage in this case is, here x is a variable, okay, and x is varying from 0 to R. Now we have to compute the work done of a particle, of a charged particle from R2 to R1. So what is the definitions of work done? Let's say dW is a small work done, which definition is F dx, right? You know this, right? What is the definitions of work done? W equals Fs. Now if we do a very small work done, dW, then it is basically F ds, and in this case our our displacement is x, so it is dx, right? Now what is F here? F is QE. So this is basically Q lambda 2 pi R epsilon naught dx x epsilon naught dx, okay? So this implies dW equals Q lambda 2 pi x epsilon naught dx. Now we have to compute the work done from R2 to R1. We will integrate both sides, and R1, R2, Q lambda 2 pi epsilon naught, these are all constant, this is dx time by x. This gives Q lambda 2 pi epsilon naught ln R2 by R1, okay? It is straightforward formula for the integral calculus. If you don't know integral calculus, then you can see my other video on integral calculus. Basically, integral calculus is required for doing the summation, okay? To compute the work done, to compute the area, etc. So the work done required to bring a charged particle Q from R2 to R1 is this.